Mate, it's a good question, only that spintrons deal with the mechanical elements and the mechanical stresses of a valve train, not so much the right timing or the velocity index. So they're really, really good for testing spring harmonics, valve lift ratios. So whenever you have huge rocker ratio engines, this is where a spintron comes into it. And you can do it with twin cams, but twin cams don't see nowhere near the valve instabilities that two valve stuff do, especially when you start talking 1.7, 1.8, 1.9 rocker ratios. That valve is accelerating really, really quickly. So the inertia mechanism and the force on it are far, far greater than, say, a quad cam bucket type engine. And we see this with Pro Stock when they start testing lofting. So with Pro Stock stuff, the acceleration ramps are that fast, they actually throw the valve up off the top of the lobe. And how well they fall on the backside is actually tested on the spintron. So they actually got what we call dynamic lift in Pro Stock. So they'll follow the lifter at lower engine speeds, but at those big, plus 10,000 RPM lobes, they'll actually start to loft and leave the lifter and actually increase the lift and catch the down ramp. And how well they do it, the spring pressures are dialed in off the spintron. So yeah, it is a good tool, but it's more to do with the mechanical stresses in the valve train itself, not so much the air speeds, durations, and so on like that. When we talk about those, we're more dialing the engine in between its bidirectional side of the VE profile versus its air banking side. And I'll show you a little diagram, and hopefully this will help explain it a bit. Okay, so what we've got here is a basic horsepower and torque curve of a stock LS engine. Peak torque, 381, horsepower around 4,500, 343 horsepower. So basically our RPM scale here, and a VE curve which follows our torque curve, and it follows the torque curve for a reason. We've got our blowback phase, so everything up to peak torque, the engine is actually throwing air back up the intake runner. When I talk about a bidirectional intake track, this is what I'm talking about, the difference between our blowback stage and our air damming stage. And we see this with LS and long-run-it engines, so an engine that you'll rev past the optimal induction length. So like an LS, it'll have its stock manifolds about 16 inches on top of a 5-inch runner. So we're talking about 21 inches. And you create an air damming mechanism that will tend to cause valve float, because what actually happens is once we get past this optimal fill point, the piston speed becomes too quick that the air can't get into the engine quick enough. And this is where we see a depreciation in our VE curve and our torque curve. Remembering, horsepower is calculated off torque. We don't actually physically measure horsepower. We're calculating it off our torque curve, and our torque curve is directly related to our VE curve. That's because the ability to fill the cylinder and create the bang, the fire, the pressure is obviously what's going to drive our torque mechanism. So this split between the two is where we've got to dial that camshaft in, get that intake valve timing closing at the right point, and also get the engine breathing right. And it all comes down to the primary induction, the camshaft, the cylinder head flow, how well it flows, and how much inertia it actually optimizes. So, but yeah, this is a big thing. And once you start understanding the difference between our blowback, so a big heavy V8 with a big camshaft, and you hear it, boom, 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 that's because it's actually blowing air back up the intake. And we see this when we pull an intake manifold off the carbon and so on. So it's very important to dial obviously the camshaft in with the converter and get the engine into its working area, which we sort of want to be, 1,500 to 2,000 past our torque curve. That's our optimal area where we want to operate the engine. If we start revving it too far, we get this air damming mechanism that can cause seat instability, valve bounce, and so on, even if the spring pressure is right. So we've seen engines where they actually valve bounce with the wrong manifold. We get the right manifold on, and they're no longer valve bouncing. So yeah, there's a lot that goes into it, but the spintron itself is more to do with the mechanical stability mechanisms of our complete valve train, push rod weights, rocker rates, and then also the rocker itself. weight on the side of the nose is far more important than weight on the back end of the rocker system. That's a whole nother video. But yeah, basically, Spintron is for your mechanical. When I'm talking camshaft design, it's all about how the engine breathes. And as we improve, like this torque curve here, many people have dynoed LS engines. If we change the cylinder head, it's going to move the torque up, move the horsepower up. That's because we've changed the velocity restriction in the head. It's all about the airspeed in our primary induction. This is why I use velocity mathematics over everything else, because the velocity is the key, because the physics of the engine is limited by airspeed. And if we can optimize the airspeed like we do with compression is the same thing. We want to squeeze the fuel as hard as possible to the line of detonation. That's how we make power. This is how every race engine works. Get it as close to the point of detonation, but stay under it. Airspeed is exactly the same. Get the primary induction length working as fast as possible without density thinning. But yeah, anyway, hopefully that helps.